Yeah, so hello, I am Arild Waaler. I am professor in informatics at the University of Oslo. I brought with me Erlend Fjøsna, a multidisciplinary domain expert with, I think, decades of experience.
Decades.
From the industry, from this industry. And Martin Skjæveland, a colleague of mine at UIO. I think very few people like Martin has hands-on experience with semantic technologies and knowledge graphs over more than 20 years. I think you have.
Yeah, maybe. Yeah.
So when we, in the title, say that IMF is a logic, we mean something very specific. Engineering information presents itself in various contexts, in various forms. And each of these forms carries just a fragment of what the engineers really mean. And in IMF, we start with a very fundamental question. What is the logic that can capture this meaning? What is the structure that is behind the engineer's intention when they describe a system? How does it, how is it composed? How does it connect? How is it classified? And we try to approach this by a few fundamental principles. The first of which is that we view everything as systems. So also this pump in this figure to the right, we would view as a system with its own structure. Second, we know nothing about a system except for the ways in which it presents itself in different aspects. So, form of presentation, Erlend, you drew some images there, like a specification, an installed object, a logical location, is it up there?
Yeah. So if you refer to how we have been working together for quite a while, and you have had or you have been at the core of a team with ideas about how this could be structured. I have been the sort of the outsider with regards to this thinking, but as an engineer and domain guy, I have had lots of problems that I wanted to, or pains that I know about that I wanted to understand. And one of the results of our discussions, our dialogue, was this symbol, where I tried to understand what was the meaning behind the aspects.
And the aspects are, they have these color codes that reminiscent of this 81346 standard. But an aspect in IMF is really a collection of parameters, contextual parameters, exactly those parameters that you need to fix in order to evaluate the meaning of this appearance. So, this is what we mean by capturing the logic of engineering meaning. And when this meaning is formalized, something very powerful happens. You get a very well-structured knowledge graph, which you can do wonderful things with. You can use it as a basis for integration. You can search, navigate. You can run very powerful consistency checks. We heard about IDO. We can exploit IDO. We can refer to IDO reference data. And if the whole model uses that, we can even translate the whole model into IDO. So, very, very importantly, IMF has the aspiration to do this in a way that really scales. So, for several reasons. One of them is that we are building on the systems concept, this very scalable, recursive concept. But also, very importantly, we have the whole technology stack available. But we allow the user to interrogate at the level which the user can understand and feel comfortable. So using plain engineering natural language, they can formulate questions, and these questions can be systematically translated into queries over these knowledge graphs. And if the engineer has a question, but needs to write the Sparkle query, for instance, if that means that this guy who can Sparkle needs to understand the engineers, have the engineers understanding and understand what is asked for, you really give away a lot in terms of scalability. So I think IMF, we try to combine, I mean, deep logic and rich semantics and practicality.
Yeah, I'd like to interrogate you a bit, because if we go back to, I think the audience, some of the audience maybe have the same questions in their mind that I had at the early stage. And you know, when I came into this as an engineer and met you and the team, I had been in different situations working to, you know, how can we structure our information about the plant better and the engineering of a plant better. And at that time, it was a breakdown structure. Yeah, this is part of this is part of this, it's a system. But you had to make a choice. What kind of breakdown structure? Was it the physical things, how they fit together? Or how, you know, so there were many attempts at making breakdown structures, but they fit one purpose, but they didn't fit another purpose. And then you brought this, you know, the various aspects can have various breakdown structures. Maybe you can, you know, elaborate a bit about that.
Well, I think you see them here. Well, actually, I mean, if you look at what's here, I mean, you have this PNID, and you have reflected in different breakdown structures that are actually well connected and well.
Yes, but you say aspect, but what is actually an aspect? We have colors here, we have sort of, you know, intuitively, we can see that one aspect is about the function, or what is it about, you know, the various aspects?
So I said that the aspects are collections of variables or parameters that you need to fix to get the interpretation really sharp and correct. And one of these would be what we call the information domain. And the yellow would be focusing on the capability. The blue would be focusing on the engineering implementation. And the pink would be focusing on spatial.
Yes. So the thing is, we have moved from, at an early stage, we talked about functional aspect, product aspect, location aspect, but then we learned that it isn't that straightforward, that you need to dive deeper down and define what the aspects are made from.
Another, where we go beyond this 81346 is that we differentiate between what we call the modality. Are you really describing something actual, like the PNID could be in the operation room? Or is it a design object, is it an intended structure? Or is it atypical? Is it just a pattern that you would like to copy? It looks very much the same, but the meaning is very different. And then we have what we call the interest, which we really can tailor-make to the specific point of interest in the life cycle.
Yes, and at this stage, this made me very happy, because now I could put myself into a position of being, for instance, a maintenance engineer. I'm particularly interested, particular domain. I can construct an aspect or define an aspect which perfectly fits my interest.
You can, and you get your own breakdown structure.
Yes.
And we can keep track of everything, so it's all well connected and consistent.
So maybe also the next I want to pick your brain on is, because now that was a revelation for me. That you can break down in different aspects. You fully fulfill your need for breakdowns, depending on interest. But then topology. At that time, topology for me was a mathematical term about whether it's a a sphere or a donut or shapes. That was topology. What is topology?
Oh, the topology is really the flow of medium in various forms, crossing the system borders throughout the whole collection of systems.
Yeah, how they connect together. And
Yeah, there's no connection without the medium.
right.
And you put that together and you get the topology.
Yes. And that was, again, a powerful revelation for me, because now you could not only find your object, but you could immediately, based on this modeling principle, know what it was connected to, and you know the whole, and suddenly you have a full context. You know that that pump is not only a pump that you can find in the data sheet, but it is there for this purpose. It connects to this and this and this and this. Fantastic. So we are very passionate about IMF. Yeah.
But you have actually done a little modeling exercise, haven't you?
Sorry?
You did a little modeling exercise.
Yes. So we're running out of time soon.
Yeah.
So now we'll. This looks like a simple process, right?
There's been very much talk about PNIDs here, so
Yeah.
you don't need to explain that.
This is PNID, PFD-ish. Someone has tied in a new gas reservoir. You get hot gas on board. It's too hot. You need to cool it. Okay, so you have an intended capability that you want to have, which is a cooler. You run the gas in there. You cool it. You dump your heat into the sea. It starts very easy, but very quickly it becomes a mess. When you add up, we saw earlier today that the SCD was put on top of the PNID. Here you have that on top, you have the area, you have the systems that talk. It becomes very messy, but using conventional.
All of these have their own identifier systems also.
And everyone has their own identifiers. Look at these guys here, these gas detectors. They are coded based on area. There's nothing about that it's related to the gas system. No, different. And the line numbers have their own. It's a mess of identifiers. So if you want to know anything about, say, this pump and its surroundings, you have to operate on very different identifier systems, unless you know how they are related.
So can we use this approach also to keep track of all our identifier systems?
Yes, we can.
Wow, brilliant.
Because we know
Brilliant.
how they are tied together. 7 minutes. So let's attack this simple, not so simple process. This is about the intended capability. This is one aspect. We want to define the intended capability. And at the top level, the thing is, you can decide yourself what kind of granularity. How do you want to zoom into the very details, or are you kind of an arrogant concept engineer who says, I just want 2 megawatt of heat removed from that gas flow and dump it into the sea? Well, then you have just one, you just have one block like this, and you define your intended capability parameters in that block. Or maybe you want to develop it further. You say, okay, I need a couple of heat exchanger, pump, tank, etc. You move down there. And then you dump this into the real engineers. They need to figure out, specify a solution for this. So now we're in a different aspect. This is the product aspect. I mean, we're looking at the exact same thing, but we're looking with different filters in front of our eyes. And then you start building up the specification, the intended implementation of this solution. And then you need to arrange this in space. And you need to pay attention not only to the architects who decide what room and deck is available, but also to the more safety-minded people who define the logical areas with regards to, explosion, gas detection, etc. So this is the location, space, and area aspect, right? They are not living their separate lives. They're in one model, one model, and they are tied together like this. You can see the dotted lines, and so for one pump, you can say what was the intended capability, what is the specification, what is the location information. And then you have the full picture of this. Right, now we know everything. Not only we, but the computer, because this is a computer understandable format. It's IMF.
But can you use it for something, Arild? Can you ask
Can
questions?
we use it for something?
No.
No.
Let's see.
I insist we can use it for something.
Yes.
So I'm
That's a good
desperate. I'm a
cliffhanger.
very nervous operator early, at work, and then there's a gas detector beeping, beep, beep, beep. What do? The gas is detected by a sensor. What's the potential leak?
Yes, what do you do? Well, IMF is not only a modeling language, but we like to call IMF a family of languages. So we have the visual language that we have seen so far, but this visual language is not informal, it's very formal. And this allows us to translate visual models like we have seen so far. We have a tool that you can build your models. We can transform that into knowledge graph. And the knowledge graph is a formal representation of knowledge that we can query. Now this is a big mess, and even though it's just a small model. So in order to make to organize this mess, we have the IMF OWL ontology. That gives us classes where we can organize the messy cloud you just saw. And the OWL ontology also allows us to do semantic verification of the content. And from that representation, we also translate that into an IDO ontology, as Paul explained. This allows us to leverage the semantics of IDO to do semantic verification of the model according to the IDO semantics. And also to support the data containers that we saw yesterday, we can translate an IMF model into AES shells. And this is to support data exchange in industry. So your question, Erlend, was?
What are the possible sources of leakage since my detector is beeping?
And how can what we just saw help? Well, since we now have a language which is completely formal, I can write my query using a graph, call it a graph navigation question. And on the top here, you see how I navigate the IMF vocabulary to find the leakage. And this is my, sorry, I'm not tall enough, but this is my product variable. And so I start with the tag, which is AP0, and I navigate to the product. And then I extract the information I want from the product, which is the tag and the name and the terminals that have a possible leakage. The way this is done is by requiring that the terminals, which represent the in and outputs of my system, have the same medium as the gas which was detected. There you have it.
Thank you. I'll run down and check that gasket.
So how can others make use of the IMF framework? Well, we have published everything open source. We packaged this in a set of tools which we call the IMF Workbench. And with this, you can transform between all these languages in our family. You can do validation using Shackle, you can do reasoning using OWL, and you can query like we saw using Shackle. And you can transform the semantic web formats back to GraphML, which allows you to do the visualization again. And with that, Arild, would you like to finish?
Yeah. So we made a brilliant web page for this event where we summarized everything that you heard today and more. And we also write what you can expect to find in the next release of the IMF manual, which will come early next year. And for those of you who can't wait to see that web page, pick up your phone, scan the image, and off you go. I think we're done.
Yay!
Yeah.
So we have minus 5 seconds for questions.
Very good.
Okay, just have 1 minute for questions, but then we need to be crisp.
I noticed you used the 81346 class codes for the function. You didn't though for product location.
I mean, you mean the color codes? Oh yeah, the class codes. Yes. So we are not married to 81346 class classification codes. We can use them, but for process classes we use the XP process, which is what the process engineers would like to use, and we use GFOS. I think for the bluish types.
Yeah.
So
maybe also said that we are strongly inspired by 81346, but we have moved on. We've further developed it. So yeah.
So IMF is made as a framework that allows you to connect to different reference data libraries, not only the RDS codes, but PCA codes, reference data libraries or GFOS or whatnot. Yes.
Hi. Not really a question, but more of a quick comment. I really like this initiative because it is one of the few in a very complex space that actually lowers the barriers for entry. Like it was mentioned earlier today, most of us are not ontologists. The engineers are never going to be ontologists, and then we need to lower the barrier of entry to actually get any use. This is one of the few things that actually takes that seriously. Super work.
Thank you.